Thanks to the organizing committee and Kathleen for arranging this and this opportunity to bring some light to this important matter. So I'm going to talk about materials for infrared optics, primarily germanium, but other crystalline materials, with a special focus on the resilience of the supply chain for this. Also a bit about LightPath. We're about 30 years old, publicly traded company, manufacturing in the US, Latvia, and China. About $40 million of revenue, 300 employees globally, vertically integrated. We produce about 4 million lenses a year, and we have the capacity to produce up to 10 tons of infrared glass a year. So the last few years we've seen a lot of growth in infrared imaging. Part of us, those in the business and working there, have experienced it as part of our day-to-day work. The rest of us, unfortunately, got to experience it about 2 years ago when the world started measuring temperature of everyone. Contactless temperature measurement created a very big growth in infrared imaging around the year 2020, as can be seen here. Although that has declined, what it did bring is an acceleration of the development of the related technologies even more. And so the reduction in cost of the imagers, the focal plane arrays, the microbolometers has accelerated further. It started about 2014 with uncooled microbolometers showing, but has really now taken off even more. And we're now seeing applications for this in many other places, including our day-to-day life, but soon to be in automotive, surveillance, and other places outside the aerospace and defense. Looking at applications, we see that in 2020, really the thermography, the contactless temperature measurement, has overtaken even the defense in terms of spending. That has since already declined to more like normal, but still contactless temperature measurement devices, as well as many other applications, are growing even faster than what spending in defense is growing, with a conservative, I'd say, 9% annual growth rate for this area. This is all great, except for the materials. The main materials used in infrared imaging are crystalline and primarily germanium. Germanium comes from the mines, mostly in Russia and China. The US imports 95% of its germanium from those two places, 2/3 from China, and up to a while ago, about 15% from Russia. There's also limitations in how it can be fabricated, size, and a very big dependence on pricing. We see big price fluctuations over years, and not to mention the obvious that our defense industry relies on material coming from outside. These are from US Geological Survey and also from a special report to Congress that was done about 3 years ago. The amount of imports in terms of value to the US in billions of dollars of germanium, as well as the distribution of it. Just to give a point of view, 30,000 metric tons of germanium are imported into the US every year. A quarter of that, about 7,000 to 8,000 metric tons, are used just for optics, not to mention fiber optics, semiconductors, and many other important topics. I'm going to focus on fiber optics because that is where we have a solution for that. About a year and a half ago, when President Biden took office, he issued an executive order to develop the resilience of supply chains in the US. In the 100-day report of that executive order and the work done, germanium was mentioned 5 different times in the report. An alternative to germanium is chalcogenide glass. It's synthetically produced. You can have much more stable costs to it. You can make it here in the USA, as we do. It lends itself also to more mass production technologies, such as molding into shape. We at LightPath mold chalcogenide directly into final lenses form. You can optimize it and have different refractive indexes and thermal behaviors and other important properties. It transmits over a large wavelength, a large range of wavelengths, and also other benefits such as athermal and lower density, translating to lower weight of the optics. Current state is there's about 5 types of chalcogenide glass commercially available. Two are really being produced, one of them in mass, another one less. Limited manufacturing capacity in the US. We produce in the US. There's at least one more company we know that has some manufacturing capacity in the US. The rest is China and Germany, as far as we know. We're working to ensure manufacturing readiness and stable production of those, and this is critical for acceptance of the materials. The material has existed for a long time. Many people in this room know far more than I do about this, and it is one of the classic cases of a very promising optical material, a very promising technology that has not been fully accepted. Part of the reason for that is information, manufacturing readiness, statistical data, stability, much more than that. There's a low market adoption because of that. Glass recycling is another topic that's important. Earlier was discussed recycling of regular silica glasses. Well, germanium can be almost 100% recycled. That's an advantage it has. You can pick up all the scrap, all the dust, everything, and regrow a crystal out of it. This does not exist yet in chalcogenide, although there is important work being done on it. About us, we're located in Orlando, Florida, or headquartered in Orlando. We have about 9 years of experience of producing chalcogenide glass, capacity up to 10 metric tons a year. We know the number is true because we put it to test 2 years ago during the beginning of the pandemic. We simply could not make enough glass to build contactless temperature measurement devices. It was a very interesting time. Vertically integrated, we make the glass, produce it all the way to final assemblies, zoom lenses, imaging subsystems. We were recently awarded the exclusive license by Navy Research Lab to commercialize the chalcogenide materials they've been developing over the last 10 years, I believe. And we're now focused on transitioning these new materials to production and on manufacturing readiness of chalcogenide altogether. The glass portfolio we licensed from NRL, as can be seen here, has also the advantages of covering a very wide range of wavelengths. I'll talk about multispectral imaging in a minute, but that is another limitation. While focal plane arrays and imagers are becoming possible to do multispectral imaging, the materials are far more limited. We've only 5 materials pretty much in the infrared crystalline materials, and only 2 of them really covering a wide range of wavelengths with lower refractive index and other limitations. This is becoming also very important. An example of why having more materials is so important, bottom left side shows the number of glasses available just from the shot catalog alone in visible. So any one of us that's an optical designer knows that that is the way to go. You need to have a lot of selection. Top left is in the infrared, in long wave, 5 types of materials, far more limiting. And a paper here was published showing building a 3x zoom that would cover and use 21 different elements using just the classic crystalline materials. Using chalcogenides as well as some of the crystallines, this was reduced to 12 elements. That is important not only in size, but also in weight and also in sustainability of being able to produce in volume as adoption of infrared imaging happens more and more. Multispectral imaging, as I mentioned, is the ability to image multiple wavebands using 1 or 2 focal plane arrays or detectors. Bottom left side shows a pod, a standard on a military aircraft with 4 different apertures for visible, shortwave, midwave, and longwave. A focal plane array, such as ones designed today by Raytheon or Apollo Engineering or Lockheed, allows for having multiple wave bands on the same focal plane array. I just came from the DCS show in Florida, where they were demonstrating cameras that are imaging both midwave and longwave using the same focal plane array. That will not be possible to implement and to commercialize both for military and for commercial without the right materials. Chalcogenides being able to tune the parameters, as NRL has shown, as Dr. Richardson here has done, as many other people, allow to tune parameters really to achieve different refractive indexes, different temperature coefficients, and many other important parameters. Current status. There's really one composition that is properly produced by multiple manufacturers. There's a range of optical coatings that was already developed, anti-reflective, protective coatings. If we could turn the video on this, we'll see an example of protective coating. We'll try from here. Yeah. So one of the problems of chalcogenide lenses is it is a softer material. This is an example of our DLC, diamond-like carbon coating, which banging on the lens hard still comes out perfect. So the protective coating is extremely important for the adoption of chalcogenide. It has had in the past a reputation of being a soft material, and people did not like to work with it. We're working on space qualification, both with support from Space Florida and European Space Agency, together with University of Central Florida. And there is already a diverse and stable supply chain for the raw ingredients. As you see, the countries these raw ingredients come from are mostly more favorable and definitely less dependent on few unfavorable countries. Challenges ahead. It's really about adopting. It's about getting the industry, getting everyone to adopt the materials. More materials are must. I mean, we license this for a very important reason, and that is understanding that you can't do everything with one or two materials. Manufacturing readiness. Incumbent germanium has 60 years of usage of data, being to space and back, has been everywhere. Everyone is familiar and comfortable working with it. We need a lot of data on chalcogenides. We need to show the world that it is a viable alternative. Refractive index data on the different conditions, thermal, mechanical, everything, you name it, is important here. More coatings need to be designed. Part of the challenges with the other chalcogenides that existed before was the difficulty to coat them. It needs to be designed in by engineers. DoD needs to give less waivers on materials coming from China and Russia. We experience it firsthand. LightPath produces optics made of germanium today and receives left, right, and center waivers to use materials coming from China and Russia. And capacity. US imports 7,500 metric tons a year of germanium. We produce at LightPath 10 metric tons. And I believe we're the bigger producer in that part. Okay, and then just final about LightPath, as I mentioned, 35 years of optics manufacturing, have come out of really precision molding technology, origins, Geltech, part of Corning, then became LightPath. For years was really focused at that, a lot of telecom, a lot of very high volume precision molding, 4 million lenses a year being molded in our facilities. We began pivoting to in 2016 to infrared imaging, understanding that chalcogenides are a key element there, and they can be molded into shape, and we can leverage our years of experience there. We're vertically integrated, and now we're really focused at enabling customers to make the most out of infrared imaging. Thank you.